Oh, a couple things here this morning as we're going to get stuff fired up. Game plan for today is we're going to finish up chapter 5. If everything goes well, we'll have a moment to jump on into chapter 6, which I think, as y'all know, is going to be the last of the chapters that we're going to be looking at for the course. So we're bringing it in for a landing. We're just going to finish up chapter 5 here by finishing, or not finishing, but doing a couple more problems dealing with distributed loads. And like I said, I think we'll have time to jump into chapter 6 for a few minutes. If there's anybody in the room who was not with us Monday, I guess that's where we're at. Today's Thursday. Wasn't with us on Monday and you didn't get your exam back, make sure and stop and see me when all is said and done. And there's a few of you that also reached out by email with some odds and ends questions, which are great. Make sure if you've got questions, stop and speak with me after class is over. We'll have plenty of time for that. We're well ahead of the end of the period, so time for that. Before we jump into this, does anybody have any questions about anything having to do with the stuff we've been covering lately, or where things are going right now, or anything at all? Okay, good. Let's jump on into, again, distributed loads. So you see a case example up here of a linear distributed load, not uniform, linear slope in this particular case right here, in other words, triangular. Distributed load acting upon a beam, as we see right here. Now, this beam is an interesting one, folks. We haven't seen this kind of loading, or supporting, I should say, not loading, but this kind of support ever before. But there's nothing in this that's a surprise. If you look at this, this is merely a beam that's resting on some kind of a roller right here and some kind of a roller right there, which, by the way, implies the beam would be free to move horizontally like so. We don't anticipate it's going to, but as you can see, it's loaded up right there with the load. I think the request on this one here, folks, I just finished off the coordinate axis system looking at the narrative in the, from the book here. The request is for us to calculate the reactions at B for the beam load as shown. I want to start off with this particular problem here, folks, because really, this one is just about as straightforward as you can get when it comes to distributed loads. Let's remember that on Monday, we saw a case of a distributed load in which the form of the load was actually made of a composite of two common shapes. One was rectangular, and if you recall, there was a triangular shape up on top of that rectangular shape. If we go back and remember what our strategy is here, folks, our strategy for each distributed load is to convert the distributed load into its point load equivalent, in which the magnitude of that equivalent is nothing more than the area under that curve. So when we think about a rectangular shape, if we know the magnitude of that force, that per spatial unit force, which is our case with distributeds, in other words, if we know the height and we know the width, then the magnitude is nothing more than height times width. That's the area of a rectangle. When we had a triangular version of that, area of a triangle is 1/2 times the base times the height, and we use that to calculate those equivalent magnitudes of the point forces. And then the only other thing that we did after that was to remember that for each one of those calculated magnitude of equivalent forces, in other words, each one of those arrows that came out of that, that arrow passed through the centroid of that common shape. So again, recalling what we did back on Monday, we had that rectangular version. We figured out what the equivalent load of that one was, which I remember was like 1,875 pounds. And that single arrow went through the centroid of the rectangle. Then we figured out 500 pounds for the triangle, and that one passed through the centroid of the triangle. It's really just that. And then after we've got that, in other words, after we've dumped this and went back to something that is nothing more than single arrow point loads on the beam, the most important thing for us to remember, folks, the thing that you want to be talking to yourself about, is just to remember, now I know exactly what to do with this. So that's the key. Our goal is just to get back to what we already know how to do. In this particular case right here, it's simplified. We have a single distributed load here. There's no composite of a multiplicity of shapes, although we could certainly do that if we wanted to. But there is no composite of a multiplicity of shapes right here. We just got this one triangular shape acting on the beam. So what do we do about this? The goal, by the way, is again to solve for the reaction forces at A and B. So I want you to think about, as you're seeing this right here, just think about, again, we talked about this before the midterm, we're in territory here if we're just not seeing anything new. At this stage of the game, we should just be in kind of autopilot mode. Like, what do we do to solve this? Okay, we start with free body. So let's do a free body diagram of the beam. Let's apply the reaction forces that we're looking for. Now, we know we got a roller right here, folks. From the earliest part of this course, we've always modeled roller forces as a single force normal to the plane of application. That hasn't changed one bit. So here, I'm going to have some force on this that may look something like this. I'm simply going to call it force A. Over here for roller B, same thing, nothing's new here, it's just a roller. So that means I'm going to have some force over here called, maybe let's call it B. Now, as we've said now many times over, do we know that that's the right directionality of these forces? No. Do we care? No. We just apply them as they are. So that's taking care of the force here, the force right here, and then we just need to take care of the triangular force. So as we go back over and we think about what that is, the triangle that we see that makes up the envelope of this distributed load right here has a base, according to that dimension right there, has a base of 12. It has a height, working up from the x-axis here, of 400 pounds per foot. And by the way, this is 12 feet. This is a height equivalency of 400 pounds per foot. The area of this would be 1/2 the base times the height, which is therefore 1/2 of our base, 12 feet. Height, 400 pounds per foot. It's just that. So in this case here, 200 times 12 is what? 2,400, right? 200 times 12 is 2,400. So that means that over here, we're going to have a single force pressing down on the beam that has a magnitude of 2,400 pounds. The where does it go in other words, is it must pass through the centroid of the shape. And as we've already talked about from our earliest explorations of chapter 5, the centroid of a triangle, look at this triangle carefully here, folks, and just always remember, from the flat edge of the triangle over to the centroid, from the flat edge over to the centroid will always be 1/3 of the base. If we were coming at it the other direction, in other words from here over to the centroid, well that'd be 2/3 of the base obviously, but for, in this case here, the flat edge is nicely right along the y-axis. So 1/3 of 12 feet, in other words 4 feet. So in this case here, we can come back and note that the distance from this edge to here is 4 feet. And then we probably can add in a few other things. So where's the distance over this A? Well, we know that's 12 foot there. Now you're looking at this and realizing that unlike a lot of the free body diagrams, I'm adding some dimensions to this. Does that matter? Not at all. I'm doing it because I choose to do it this time, because I can do it this time, and it doesn't hurt to have a reference of, well, where are these things all at? So from here over to here, another 6 feet, no problem. Now we know where everything's at. Now if you look at this, we have in front of us the same old. Nothing's new here. Now we've got a free body diagram, 2 unknown forces, 1 given force. Let's just solve the problem. In this case right here, if we sum forces in the x direction, folks, I'm not even going to write it down. If we look at this visually, if we sum forces in the x direction, there are no forces in the x direction, so we don't need to worry about that. If we sum forces now in the y direction, we are going to have A minus B, it's minus B because it's going in negative y, minus 2,400. And that must be equal to 0, which means we believe that A minus B would therefore be equal to 2,400. Can't solve it, but we certainly can once we do a moment equation. So now, let's sum up moments. Always reminding ourselves that counterclockwise is positive, knowing that we can pick any place that we want to for doing that moment. Folks, for me, I'm thinking I want to pick a place where I'm going to get rid of one of my unknowns and make a simple equation, right? So how about maybe we take the moment about point A. If we do that, then we're going to get rid of this force here, and we'll have a moment equation that includes B and includes the 2,400. We could, if we wanted to, take the moment about B. So in that case, we have the A force and the 2,400 involved. It doesn't matter. We're going to get the same result either way. Let's just choose A in this case here, folks. Random pick, but just choosing A. So now, from point A, over to the line of action of force B. So we look at B here. We know that our moment center is here at A. So B with respect to the moment center is doing a clockwise rotation, therefore it's negative. So minus B times the moment arm from A over to the line of action of B is 6. Takes care of that one. Now as we look at this 2,400 pound force over here, again with respect to the moment arm at A, we see that that one is going to cause a counterclockwise rotation, therefore it's positive. So plus 2,400, and now we need to look at that moment arm. Well folks, the moment arm from here to here is going to be 8, because if you think about this, from here to the edge is 12, but we're coming back 4 from the edge, so from here to here has to be 8. So 2,400 times 8, and this is equal to 0. So now with all said and done, we're going to find from this equation here that B is therefore now going to be equal to 2,400 times 8 divided by 6. And that, folks, let's see, 2,400 divided by 6 is 400. 400 times 8 is 3,200. So right now I have B is equal to 3,200 pounds. If I bring this now up to here, we're going to have, from this equation, we got A minus B, so minus 3,200 is equal to 2,400. And it's a pretty quick thing here to see that A then, as I move the 3,200 over to the other side of the equal sign, becomes positive. So therefore A is equal to 5,600 pounds. And with that, the problem is solved. Just like that. The big takeaway here, folks, and my hope as I'm looking at the audience right now, as I'm seeing faces like, yeah, I get this. This is pretty straightforward. It's meant to be. My hope is that by the time we got here, you're seeing absolutely nothing that yet you don't already know how to do. The only thing we got to worry about is the conversion of the distributed loads. Does anybody have any questions about that particular problem right here? Okay, cool. Let's do at least one more. Got a couple I'm actually kind of interested in doing, so we'll see how it goes. Okay. A few seconds to get it drawn up.
I have a question.
Yes.
So for the center of the triangle,
Yeah.
I forget exactly how I did that, or do we just, yeah, so how exactly do we find the center of the triangle?
Yeah. So a couple of things, and the answer's got kind of a part A and a part B. Remember a couple of visits ago, we actually derived it, right? So we derived that it was 1/3 of the base. That's one. But I think the more important, the salient thing is remember that we're not expected to remember that, right? But you got, in your book, you got an appendix in the back that's going to show you a triangle and remind you that it's base over 3. And if we're looking at height-wise, it's height over 3 as well. Both of those measures being taken, though, importantly, from the flat edges of the triangle.
Okay.
Did that take care of you?
Yeah.
Good. Kenny? Oh, I can't hear you, sorry. Great question. So Nate's question is, so make sure everybody hears it. Does the Y direction matter? So Nate, to your question, we know that the Y location of the centroid is somewhere up like where my finger is, right? Well, but the reality is the force passes through that centroid wherever it is. So it doesn't matter where the height is, because we know that what does matter is this location right here. It's a great question. What other questions might you guys have? Good stuff. See, these are the kinds of questions that are really helpful. Yeah, fire away.
And if the equivalent force was horizontal, then the exponent wouldn't matter of the centroid. If the equivalent force was horizontal instead of vertical, like it is up there,
Yeah.
would the exponent not be useful for the centroid?
I think I understand your question.
So like how we only use the x component there in the centroid, we would
Yeah.
only use the y component if it was a horizontal.
Yeah, and I'm gonna do a quick example of something where that might be a thing, right? So let's say that I had a beam that looked like this, right? And on that beam, let's say that I've got, I don't know, let's say I got a distributed load that looks like this here. and let's say I got another distributed load over here that looks something like this, right? In this case over here, I would be interested in that case of the, no, actually I wouldn't be interested in the height of that. I would still be interested in where it is this way because I need to locate the force, but I still don't care where it is height-wise from its point of application. So I can't think of any scenario where the height does matter. Yeah. Although you did. I think you did. Because if I'm hearing you, I think you're contemplating, well, what if I've got, and you know, stop me if I'm wrong, but what if I've got a force, a distributed load that looks something like, and folks just forgive me, I'm doing some spur of the moment artwork here, because I think this question's great, by the way. What if I've got a distributed load that looks something like this? All right, now I would have to look at, okay, where's the height of this and where is the centroid this way? Because that force has to pass through that centroid point. Yes, even then, if you think about it, if we know where the height of that is, then we know that the equivalent force has to pass through that. So I still don't think it's necessary. Let's put it this way. I've been doing this a long time, and I don't recall ever having to care about where the height was. It's not to say it's not impossible, but I don't remember seeing anything in which that was the case. But it's a fantastic question. Thank you for it. Again, great questions. This is good stuff. Anything else, anybody? Yeah, Nate, far away.
Would we see a problem like the one on
Over here?
Yeah.
Would you see a problem like that? I think the short answer is yeah, because there's no reason not to. So let's just let's play with this. I mean, I wasn't planning on doing something like this, but let's just take a quick peek at what that might look like. Let's say, if you guys are if you guys are cool with not getting carried away with the artwork here, let's say that I have a beam like what we're looking at right now, and let's say there's a pin on this beam, and let's say there's a roller over here. And let's say that, I don't know, let's call this pin A and roller B. Let's say my goal here was to figure out what the reaction forces are on A and B, right? So let's just play with that scenario. In this case, and this is why, again, it's so important just to follow the standard plan. It's one of the things I don't think we say enough in this course, is that dealing with something we haven't seen before is just a matter of just doing what we always did. Nothing really changes, right? So in this case here, I would have a free body diagram of this beam that would include the pinhole right here, so that's what the beam would look like. And so if you think about now what the free body would look like, I've got a pin here at A, so in the, again, nothing's new department, I'd have like an AY, maybe some sort of an AX on it like that. Over here at the roller for B, I would have a single force for the roller on B. So again, think about this. Never mind the fact that the beam is L-shaped like this. Never mind that at all. But notice here, the free body diagram for the pin, the roller, is just the same old, nothing's new, right? Now, but to Nate's question, what would we do if we had that? So now, if you look at, here's our free body, pin and roller forces. I got a triangular distributed load up here, which I'm going to convert this. I'm going to do it on this original diagram just to illustrate the point. I know that I got to figure out the area under this curve, and I need to pass the single point load through the centroid of that. So I know I'm going to have a single force going through something like that, right? So in this case here, when I do this on my free body, here's my single force. So I don't know, let's call this L1 for lack of anything better to call it. And then over here, I've got a rectangular shape, right? And I know that I'm going to convert this into a point load by taking the area of that rectangle, right? So we know this distance here, we know this height, and nothing's new. And then that's going to pass through the centroid of that, so that's going to become a single load that's going to look like this. So let's put that on here. We'll call that one, let's call this one L2. Just again, just making up some stuff as I go with this. So now if you look at what we got here, folks, we would presumably know the value of L2. I mean, that's the whole idea. We get the value of these things. So we got those two values. And now we're back to a free body diagram that if I sum forces in the x direction, I'll have L2 minus AX, so now I know what AX is, right? If I sum forces in the y direction, I got AY plus B minus that equals 0, and I can do a moment equation anywhere, get my moments, and I figure out what all those are. So to your question, Nate, and it's a great question again, would we possibly see something like this? Sure, it's certainly possible. Am I planning on it? No, not really, but it might, you know, who knows. But even if you did, it's just the process is the same. There's just nothing new. It's a great question. Again, folks, these are good. What other questions might you have? Cool, let's take a look at one more then. All right, folks, so check this one out here. Now, think about this, folks, as I read the narrative on this one, just think about this again. If you were attacking this problem right now, what's your plan, right? The answer is, I start with a free body diagram. All right, it's always that. That's always the answer to what's the plan. So check this one out here. Find the reaction at A due to the uniform loading and the applied couple. So what's different about this one here, folks, is we've seen this before. And as we should remember, this is not a big deal, but in this case here, we're applying a couple, meaning there's something causing this beam to try to be rotated by this couple right here. This we've seen as well. This is the rigid mount, all right, the old diving board, the cantilevered beam kind of a mount right here. So, as I said, how do we do this? Let's start with the same old, nothing's new here, free body diagram of the beam. The beam itself is going to now have possible forces back here where it's supported. Right now, think about this. If we don't remember off the top of our heads how the forces would look on this, when you're not certain, you can always ask yourself, hey, if I were to, and let me throw an XY axis onto this thing here real quick, folks, just so we got that. If I were to try to move this beam in the X direction, if that thing is solidly mounted in here, would I face resistance to that motion? Of course you would. So if you're going to face resistance to that motion, then there's going to be some sort of a force there. Let's assume that that's force AX. If you try to move this beam up and down in the Y direction, will you face resistance to motion? Yup. So therefore, there's going to be some sort of an AY associated with that. Let's call it AY right here. Now, also very importantly, if you took this beam, this real life beam, and you tried to rotate it around point A right here, with that thing solidly locked in, would you face resistance to rotation? Yes, you would. So since you're facing resistance to rotation, then we can assume there's going to be some sort of a moment there. In this case here, we'll just draw that as some unknown moment. I'm going to call that M sub A for the moment about A. So those, by the way, are my standard, these are the standard supports for a rigidly mounted, for a cantilevered beam, as we see right here. Again, nothing new. Now our applied forces right here. We know that there's a 7,200, 7,200 foot-pound or pound-foot couple moment, torque, whatever you want to call it, applied to that. Got it, no problem. The only thing we haven't dealt with yet is the distributed load. And I want you all to look at that distributed load and just take about 2 seconds and ask yourself, what is the magnitude? What's the equivalent magnitude of that distributed load? Is there anybody in here who did not, in those 2 seconds, I took a breath of air, that did not come up with 1,600 pounds? That could have been, I could have been funny and said 1,400. Anybody not come up with 1,400 pounds? Because I would have loved to see like, yeah, that's what I got too, Professor. All right, exactly, 1,600, right? It's just the area of the rectangle. Height, 200, width, 8. So we got 1,600 pounds, which we know is going to now show up over here as a single force, 1,600 pounds. Where is that thing located? Well, from the edge back here, as we think about where A is at, and I should have put a Y and an X in here, not that it's ultra needed here, but the centroid of the rectangle is in its geometric center. So if it's 8 wide, then the centroid's at 4. So I can come back over here on my free body. It doesn't hurt one thing at all, one bit. Just put, in this case here, 4 feet over from here to there. And voila, we now have a complete free body diagram. It's hardly worth continuing on here, folks, but I'm going to. But again, this is where we can check the box and say, do we or do we not understand how to handle distributed loads? What you're seeing right here is nothing new in the free body diagram in terms of how we represent these rigidly supported beam. Nothing new in the applied couple over here. The only thing new is how we show the distributed load. So we want to make sure we're there on that. Let's sum the forces now. So folks, if I sum forces in the x direction, I see that I got minus AX. And even though, boy, that's a busier looking free body than we're used to seeing, there is no other x direction forces on there. So that's equal to 0, meaning that even though we drew AX, AX is therefore equal to 0, nothing new. Let's sum forces now in the y direction. Here now, we have AY drawn in the positive direction, minus 1,600. And again, even though it's busy, these are the only y direction forces, so that's equal to 0. Boy, this is starting to look easy now, isn't it? So now AY is simply equal to 1,600, and we know what it is. The only thing we don't know right now, folks, is we don't know that moment about A. So let's sum moments. If we sum up moments, and again, we already know, because this is the same old, we already know that we can sum the moments about any place we want to. It doesn't make a bit of difference where. How about we just choose point A? If we choose point A, we're taking this out of the picture, that out of the picture. So I'm going to sum my moments about A, reminding myself that counterclockwise is positive. Check out the unknown MA as it was drawn. So even though AY and AX pass through point A, this moment is still present about point A, so therefore the moment shows up in the moment equation. This one here is drawn, was drawn as a clockwise moment, so therefore it's negative. So I'm going to have minus MA. I'm going to come back to this one here in just a second. I want to take care of this. If you look at this 7,200 foot or foot-pound moment down here, we see that that's drawn in a counterclockwise rotation, so therefore it's positive. So remember, we simply, for an applied moment, we simply add the moment in. You're never, ever going to multiply that by any distance because it's already a moment. Remember, a moment is a force times the distance, right? This is already a moment, so we're not going to multiply that by, in this case, 16 feet. It doesn't matter where it's at. But then we've got the 1,600 over there, folks. The 1,600 that we see over there, as we look at it, as drawn, and we find that, by the way, this is critically important. Oh, this part really is important. We found that AY, by the math, worked out to be 1600, so AY is drawn right. Well, I guess 1600 was drawn right anyway because that was a given. I guess I toddled off into some place that didn't matter. But the 1600 as drawn would cause a clockwise rotation about A, which makes it negative. So I'm going to have minus 1,600 times the moment arm from A times 4, and that's going to be equal to 0. And with that, ladies and gentlemen, we should see now that if we take MA to the other side of the equal sign, it's going to become a positive. So we should see that MA is going to be equal then to 7,200 minus, this is going to be 4 times 16. So what is that? 4 times 16 is 64, right? So minus 6,400, which is going to simply be equal to 800. So it turns out that the moment about A is going to be 800 foot-pounds. And we just solved that problem using the same old, nothing's new here. Question on it? Eliana?
Yeah, the moments around A, what did 1600 be again?
So the 1600 we have right here would be negative, right? Which is, that's why I gave it negative.
Oh, yeah, I misheard you.
Oh, yeah, okay, so all good. Questions on this one, anybody else? You see how it's starting to come together here, folks? What you should be able to see here is that, again, we're doing stuff that's new now, but it's based on a foundation of so much that's not new. All we need to do is figure out how to pick these things up. Let me think here. Is there any value in doing one more? Not really. How about you guys? Does anybody in this room want to see one more distributed load problem, or you think you got it? And again, I mean, if anybody feels I'd like to see one more, just give me a nod. Or probably give me more than a nod, I can't see it. You want to see one more? We'll do it. Let's do that. Let me clean this one up here, folks. I think I want to do one more that's consistent with what we saw on Monday, just to make sure we've really got this nailed down in terms of what happens when we've got a composite of loads. So let me grab one here. Just kind of picking one out of the crowd here. It's a little random, but let's do this. All right, once again, actually I just realized I made a mistake, hang tight. B is not another pin. That's wrong. It's drawn weird in the book, so I'm just going to simplify it here, folks. Let's just put a roller there and call it good. So now it looks more like what we're used to seeing. So, short story on this one here. We got a beam here. The ask on this one, folks, is to determine the reactions at A and B for the loading that you see shown right here, folks. And as we see in the loading in this case here, we have a composite. In this case, a composite of, as you look at this and kind of ask yourself, well, what do you see right here? I think what I'd hope everybody is looking at and seeing is that you've got a shape here that comprises a triangle, a rectangle, and another triangle on the right-hand side of that. And all these three things are brought together to make this shape right here. So if we see those individual components in this composite, then let's just solve it in the same old here, folks. And again, think same old. Be confident in that, all right? So same old means we start with a beam. Free body diagram of the beam itself. Let's just start that off. Let's get pinhole A in here, like so. Let's remind ourselves that our axis system, we got the y-axis up here. It's drawn that way up there. We can, again, we can draw it literally anywhere we want to, any way we want to. And as we look at this free body now of the beam, we think of the pin at A, and we realize that, well, there might be a X force. Bet you most of us already know there's not going to be an X force. We got AY down here, and then we've also got a force over here at roller B. So let's just call it that. Now again, I'm going to step away and look at that free body of the beam itself right here, folks. And to this point, again, there just isn't anything here we've not seen. Standard pin, standard roller, got it. But now we do have our composite shapes. It is worth noting that the triangle, the way this is drawn, the triangle is meant to be shown as ending here at point A, and this other triangle is meant to be terminating here above point B. So that means our dimensions matter. So importantly, look at this and notice, folks, that the per spatial variable magnitude, in other words, the pounds per foot in this case, or if this is SI, the newtons per meter or whatever, that this height here, this height here, this height here, they're all the same at 160 pounds per foot. So with that, I think about this triangle right here. And I know the area of this triangle is, again, 1/2 its base times its height, right? So in this case, for its force, the force associated with that, we're going to have 1/2 times the base here, which is 3, times the height here, which is 160. And folks, I'm not going to draw it over and over again, but let's make sure we're all clear. Units here, 160 pounds per foot, 3 feet, all right? So we're going to end up in pounds. So 3 times 160 is 480, half that's 240. So that means this is equal to 240 pounds. And we know that's going to be placed, very importantly, through the centroid of this triangle. Now, here's where it's critically important for us to remember that centroid is located always from the flat edges. So 1/3 of the base this way, or 2/3 of the base from the vertex over here. 1/3 of the height here, or 2/3 from that vertex up top right there. This one's really easy, folks. From this edge, if this has a base of 3, then 1